Okay, off we go. For those of you that you don't know who this gentleman is, this is Isaac Asimov. Mr. Asimov has been an infamous science fiction author who wrote more than 200 books during his career. His work has shaped the science fiction scene as we know it today and inspired movies like The Matrix. Through his books, he envisioned and predicted the future of the 21st century's robotics revolution. Although he worked as a biochemist, he could predict the technological evolution using bits and pieces of information along with his imagination. And if you may be wondering what a science fiction author has to do with a tech-related talk, bear with me for the next 20 minutes or so. So, hello everyone. It's been my honor and pleasure being with you, supporting such an amazing event. My name is Theodore and I'm a software engineer based in Athens, Greece. You can find me online on Twitter or GitHub. Please do follow me as I'm trying to build a cult and I want to share a really interesting project of mine. For the past few years, I have been digging through Asimov's work and somehow I convinced myself that our lives look alike. Not because I have any chances of writing a book, but mostly because I also love combining ideas and telling stories. And today, I'm gonna tell you my story, how I built a robot. So a few months ago, a friend of mine asked me if we could make a side project. Nothing fancy at all, just a teeny tiny time tracking application. Just for fun, we started immediately working together. We decided to rely entirely on the JavaScript ecosystem, using Node.js for the backend and React for the user's interface. And since we launched and we had some traction, we thought that it might be a good idea to play around with React Native. So after lots of trial and error, we had our two shiny mobile apps published, and this is when our saga finally begins. You see, I truly believe that good software comes hand by hand with extensive testing. This is something I learned the hard way. In the backend and the frontend, we were pretty confident releasing code to production because we had great coverage with unit and end-to-end testing. Using end-to-end testing, we could also detect anomalies and side effects and properly document any business logic. For our mobile applications, on the other hand, we had lots of unit tests in place as our design system was extensively tested. And zero end-to-end testing. And do you know why? Okay, let me tell you why. Because mobile end-to-end testing is like walking towards an erupting volcano. Although there are some automation testing frameworks around like Appium, end-to-end testing in physical devices is nearly impossible due to the security limitations of the providers. QA engineers are fighting this problem for a very long time, and we all have to agree that mobile testing is crucial. Mobile applications are tightly bound to the physical devices, and we need to ensure some standards for our products. Especially for Android users, we faced countless problems, from memory leaks up to hardware limitations. We had to test by hand that everything looked okay in devices with different resolutions and screen dimensions. We got our apps rejected numerous times because we couldn't get aligned with some devices' standards. And you have to consider that we spent countless hours for debugging, although we own a relatively simple application. Mobile testing is harsh due to reasons beyond our control. You see, mobile applications are essentially grey-boxed. We have some sort of control in the resources we own, and that's it. Thus, we can't actually establish testing flows that require interacting with any external applications, like testing a login flow with email validation. Furthermore, we can't even access the device settings or any operating system internals. We are strictly limited to what our application does. Even so, we tried and faced problems with our initial setup due to push notifications, alerts popping, and incoming calls. Testing frameworks are unable to tackle properly external disruptions or context switching. But if you think about it, this is how mobile devices are working, right? They are breathing and kicking, and it makes no sense to isolate our working environment just for our testing purposes. Furthermore, we couldn't track and analyze important metrics data. How many seconds does our application take to boot up? Does it feel slow on low-end phones? How much time does it take to download the binary from the App Store? What's the end user's experience with a 4G network? Do swipes feel snappy? These metrics are essential for marketing reasons, and we were completely blind on the spot. And last but not least, in most cases, we had to introduce ugly hacks in order to properly and precisely simulate gestures and taps without touching the screen. Events produced by Appium are always virtual and require extensive setup. And that problems kept bugging me for a while, as I was struggling to find a proper solution rather than manually testing and debugging every single change on my phone. During that period of time, I also bought my first 3D printer as I was experimenting with IoT rapid prototyping. During a printing session, as I was watching the mesmerizing effect of hot plastic traveling through space, suddenly I had an epiphany. What if I could replace the printer's content with a stylus and try to tap my phone? After all, 3D printers are fully programmable. So, I secured my phone on the printing pad using masking tape and tried to reach the screen. And all of a sudden it worked. It really worked. I was successfully producing tapping events, and I thought, that it might be a good idea to try out building an actual robot for mobile testing automation. And when someone's hearing about building a robot, they might be thinking something like the Terminator, but in reality robots are rather boring. There are plenty of white papers and open source projects available with lots of different designs based on the application area. And since the robotic applications are widely used for more than 15 years, the underlying technology is pretty mature. So we can limit down our available options and we can categorize them based on their moving mechanics. Robotic arms are used in industrial lines, and they are pretty efficient for repetitive tasks. An example of where automated robotic arms are used is in the auto manufacturing industry. But for our use case, they're not going to work, as we want more versatile and plethoric gestures and movement. Cartesian robots, also known as linear robots, are used for a wide variety of applications. Accommodating 3 motors and a linear axis system, they move an actuator, in our case a stylus, across a 3-dimensional space. 3D printers, CNC machines, pick-and-place robots, laser cutters, plotters, all of them are based on the principle of the Cartesian coordinate robot. But although these robots are pretty accurate, they are also a bit slow, and the movement does not feel natural at all. And finally, our pickup for this project are called Delta robots. Invented in the early 1980s, Delta robots are moving using multiple kinematic chains. They are powered by 3 or 4 servo motors attached to a steady base, rotating and moving the robot's arms. Delta robots have popular usage in picking and packaging in factories because they can be quite fast. Some of them are executing more than 300 picks per minute. Also, the way they move is the closest we can get in order to replicate our thumb's movement. Luckily for us, Jason Huggins, the creator of Selenium, designed and open-sourced a Delta robot used for automation testing. This project is called TapsterBot, and you can find it online on GitHub. Based on Jason's work, I forked his project and modified the design a bit. I used my 3D printer, bolts and nuts in order to reinforce the base and the arms of the robot. The arms are held in place using pairs of strong magnets, while the electronics are safely secured on the top plate. The brain of our little piece of art is running on a microcontroller. Microcontrollers are small computational units, widely available and relatively cheap, coming into the shape of a board. For Tapsterboard, we're going to use an Arduino Nano. As you can see, there are pins popping out from the device labeled with numbers. Using these pins, we can connect the motors of the robot directly to the Arduino. The device requires no external power connection as it is powered through a USB port. The USB port is also used for serial communication and programming. And when it comes to programming, we can write code for the board using the Arduino IDE and a superset of C++ functions. There is a vivid community behind the Arduino Foundation with lots of open source projects and prototypes available online. The Arduino provides us with some internal functions like the setup and the loop. Using these, along with internal libraries, we can create full-blown software running on low-level devices. For example, the code in this slide will blink an LED attached to the pin 3 within an interval of 1 second. Using the IDE, we can compile the code and upload it to the device. And although C code works great for most cases, Tapsterboard uses another approach. Under the hood, the robot is powered by Johnny 5. Johnny 5 is an open source library and a framework that allows us to remotely control the board from our development station using Node.js code. In that manner, we can pair hardware with our web browser and enhance our development experience. Moreover, we can consume modules from the NPM registry or even establish a remote connection with a robot using a web server. This part is essential as we can expand our robot using modules widely available. For example, we can use helper libraries like Lodas or even control our robot using a WebSocket library. And last but not least, Johnny 5 can work on different boards using the same code. This part is essential, as well as hardware specifications are totally different from one microcontroller to another. With Johnny 5, we can create a standalone robot on a Raspberry Pi, as Pi boards are capable of running lightweight versions of Linux. Finally, we can also run a Tapsterboard farm, as we can connect multiple robots using the same controlling station. Running Johnny 5 is really simple. Since we get the module installed, we can directly use it from our command line interface. The package will establish a new serial connection with the Arduino, and we can immediately start writing code. So, first things first, we need to require the Johnny 5 module. Using the built-in board class, we need to instantiate a new Johnny 5 board instance. When the board gets interactive, we also need to create 3 new servo instances. These ones are moving the arms. The kinematic calculations are a bit confusing and require lots of math and trigonometry, as we have to translate the servo rotations to actual movement into space. But eventually, we can consume them as an independent module provided by Tapsterboard. Using the kinematics class, we can move the stylus using a helper method, passing down the x, y, and z coordinates of the movement. If z is set to 0, the stylus is actually touching the screen. If all values are set to 0, that means we are touching the center of the screen. In this way, we can recreate simple taps and raise the stylus on demand. We can also add delays between taps as we want to create more natural interactions with the screen. Swipes can get recreated accordingly, as we can move from point A to point B within a period of time. We can even use easing effects by applying a helper method in order to manipulate the steps of the movement through time. Now that our robot can effectively tap and swipe as a human being, we need to fix one last problem. We need to ensure that the robot is aware of the actual device's position on the base. Since there is no such thing as a sensor, in order to detect the placement of the phone, we need to calibrate TabsterBot and prevent the stylus from crashing the screen. But how can we do that? Using a web server, we can effectively establish a communication channel between the phone and the robot. We need to create a simple HTML grid and start moving the stylus towards the screen. Once a tap occurs, we can read the position of the stylus. Afterwards, we will raise the actuator and repeat the process 2 more times inside the grid area. In this way, we can calculate the movement steps and precisely detect the working area of the phone and the boundaries of the screen. Now we are all set and we can start writing our first testing scenario. Since we are all set, we can pipe the output of the robot and use the Appium test executor along with a web interface. We can establish locators for UI elements and write full-blown testing scenarios with the appropriate validating assertions. In our case, we use the REST API in order to allow Appium controlling the robot. Furthermore, we can interact with popping messages or even tweak the device's settings. And finally, we're no more limited to the applications we own. We can track down the screen of the phone and run our testing scenarios against external applications. For example, in this video, TabsterBot is interacting with my Instagram feed. With the image recognition techniques, we can extract data and detect changes directly from the screen. And since there are no limitations at all, we can manually tweak the device's settings as a user would normally do. And if you ever had the chance to read Asimov's book, I, Robot, you may be aware of the 3 laws of robotics. This concept was firstly introduced in 1942 short story Runaround. These laws are describing how robots may not harm the humankind by every means, and Asimov's stories test his laws in a wide variety of circumstances, leading to proposals and rejections of modifications. Thereby, since this rule set is in place, we can safely go a bit wild with our creation without any fear. We can combine ideas and concepts that they were recently introduced to our community. So we experimented a lot recording our user sessions, and we were able to accurately simulate the recordings through TabsterBot. In that manner, we can write tests or simulate scenarios without writing any code at all. This achievement is really important because we are now able to debug a user sessions remotely or even create A/B tests in an isolated environment. Also, since taps and gestures can be expressed as vertices of coordinates through time, we can create dynamic testing scenarios using machine learning and analytics datasets. Instead of replicating our user sessions, now we can create our own artificial users on demand. We use this technique in order to simulate aggressive testing scenarios and discover side effects of the application. It was fascinating to find out that we could group our users under personas based on how they interact with the application and virtually test out new features. And if you think about it, we can even experiment a bit more with other cool ideas like artificial music composition on the piano. Based on that concept, we can create interactions with the real world. We actually have planned lots of upcoming experiments, so stay tuned, people. And finally, I also had heavily experimented with accessibility applications using TabsterBot. I truly believe that we can help people in need. Just imagine if it was possible to control your phone using eye movements and a web camera, or if we could develop homemade assistive hardware for people with Parkinson's disease. We can effectively and directly help people using common web technologies and widely available hardware. This idea is just fascinating. And if there is something that you can take away from this talk, is the fact that you can do whatever you want to do, using the power coming from this community. It doesn't matter who you are, it doesn't matter where are you coming from. We want to give you the tools, the knowledge and the assets to achieve your dreams. You can be whoever you want to be. We are part of the most popular tech community of the world, and our power is endless. The theme of this online conference is presenting to you what's next for the JavaScript ecosystem in the upcoming years. I honestly cannot predict the future, but I can safely say that every time you need us, we got your back. We can provide you with the ideas and the inspiration to chase your dreams. And as a matter of fact, we do actually care for one another, and we can help one another by any means. In that manner, the future is bright, and I'm pretty sure about that. Together, we can build our own robots, and who knows, maybe one day they would break Asimov's laws and rule this world. Thanks so much for your time and patience. Please stay safe, everyone. Now we need you more than ever. Greetings from Greece. Bye.